Okay, we are live now.
Thank you. Hello, everyone, and a very good evening. This is El Shalini representing Rand Publishers, and I'm glad to welcome you all to today's webinar session on the topic Innovation for Better Tomorrow. I would like to thank all the participants for taking the time out and being here today. And I would like to remind you all that today's session is the beginning of a 3-day webinar series. Let me now welcome Dr. Rani Christina, who is a part of Ryan Publisher Group, currently working in a COVID facility lab. She is the convener of this webinar, and I would now request Dr. Rani to speak a few words with us. Over to Dr. Rani.
Thank you, Shalini. I welcome one and all to this webinar, and I hope you find this interesting. So we have organized this 3-day webinar on nanotechnology. So it focuses on applications and the recent developments in nanotechnology. And we have 3 speakers, Dr. Vinod, Dr. Sasha, and Dr. Ganesh Mani for the next 3 days. And today we start with Dr. Vinod Kumari, who is joining us from Israel. And I leave it to Shalini. She will be highlighting his achievements and his nature of work. So kindly make use of this webinar, and we'll have a lot of time to ask questions and leave feedback. Thank you very much.
Thank you, Dr. Rani. And this is just a small reminder for all our participants. Today's session is the beginning of a 3-day webinar series, and the feedback form link will be posted on the last consecutive day, which is the 6th of October 2020. And now, without further ado, I would like to introduce our resource person, Dr. Vinod Kumari. Welcome, sir. Dr. Vinod has completed his undergraduate studies from Scott Christian College, Nagarcoil, India, and his postgraduate from VIT University, Vellore. He has obtained a PhD degree in chemistry, nanoscience, and nanomaterials from Shastra Deemed University, Tanjore, India. Currently, Dr. Vinod is pursuing his postdoctoral studies in environmental engineering, Tel Aviv University School of Mechanical Engineering, Israel. He is actively involved in various fields of scientific research, which includes visible light nano photocatalyst, membrane development, water treatment, electrophoretic deposition, advanced oxidation process AOP, chemosensor, biosensor, electrochemical sensor. I would now like to highlight his relevant skills and attributes, which includes ozonation technology, material synthesis, powder X-ray, diffraction, PET and beta analysis, physicochemical water, quality measurement, atomic absorption, electrophoretic deposition and membrane treatment. Further, adding up to his expertise, Dr. Vinod holds professional honors, awards and fellowships, as well as several scientific publications. I would now like to request Dr. Vinod Kumari to take over this session. Over to you, sir.
Okay. So I can share my screen by now. Shalini? Hello?
Sure, sir. You can share your screen right now.
Yeah.
I would further like to request the participants to be more interactive with our resource person. and kindly post your queries or comments in the comment section. The slide
Okay.
is visible, sir.
Thank you. So, good evening, everyone. It's Vinod from Israel. And thank you, Charlie, for a wonderful introduction. And thank you, Stevie, for organizing this wonderful webinar. And also the convener, Renee Christina, thank you for inviting for this section. So, to start with, I would like to introduce much more in detail. So I have done my PhD from Sastra, as Shalini said, but also I'm working right now in Tel Aviv on developing water treatment technologies on visible photocatalysis. And so to start with, I am currently working in Water Tech Laboratory in Professor Hadas Mamin lab. And she is a wonderful supervisor, and it's been almost 3 years working in the same lab. And we are more focused on the bullet points with the objectives which I have mentioned here. The themes, which is really a broad theme. So I would like to summarize one by one. So to start with, we are right now working on developing alcohols for hand sanitizers from biomass using ozone technology. So as we all know, like Israel is one of the startup nation. So, and but what we do is like we don't have our own ethanol production. So we need to import the ethanol from the other countries. So during this period, these pandemic situations, we thought to develop the ethanol productions from biomass, which is surplus in our own society nearby, and we're using the ozone technology in much more cost-effective manner. So this is a very, very, very new theme which right now we are working on this situation right now, and we are also in media and the news around for taking this step forward. And we are right now making this into a pilot scale system, and hopefully we will have a good results in the upcoming months. So the second theme is on UV LED. So okay, yeah. So about the UV LED technology for disinfection studies, Professor Hadas has been a expertise and completely equipped with the LED systems from past one decade. So we right now are working on a different multifunctional LED wavelengths for disinfecting biological systems. So again, the pandemic situation, like the COVID time, we do have a research on working on HCOV 43. It's a coronavirus strain, and we also publish this results in very photochemistry journal, Photochemistry A/B. So very recently this research was done, and now we are more towards heading on to working with real corona COVID-19 strains. So the third point is the metal-free photocatalyst, which is more on my expertise, and I am working mostly on this part to develop a metal-free photocatalysis for degrading estrogens and pharmaceutical drugs, which is present in real wastewater streams. So here, the estrogen, which I'm gonna talk much more in the upcoming slides, it's one of the emerging contaminants and already existing in the real waters. Even after the treated wastewater, you can find this estrogen hormone. It's a endocrine disrupting hormone. So it's a very, very, very problematic hormone. And the pharmaceutical drugs, again, when you work with hospital wastewater, you can find many pharmaceutical drugs excreted from patients. So again, after the treatment process, you can still find the existence of these pharmaceutical drugs in nanograms or ppb levels. So what we do is we synthesize a novel photocatalyst, and then to my fourth point, we take this catalyst into a membrane reactor. We enable or we make it into a system of this photocatalytic membrane reactor and demonstrate this photocatalytic remediation. So this is a complete unit, like to synthesize a material and not using that as a powder phase, whereas to make into a membrane, like a system which will not itch off during the treatment process, and you can regenerate and recycle the whole process again and again. And my fifth point is on textile wastewater treatment. Here we work with indigo dye wastewaters, which is mostly a problems with denim jeans. We know, like denim industries, they circulate these indigo dyes, and there is a problem to regenerate or remove these colorants from the wastewater, and you cannot put this wastewater as such or dump in the wastewater as such into the environment. You need to treat this wastewater. So before you, if these effluents get into the environment, you need to give a treatment, and this treatment is very cost effective right now. They use electrocoagulations, they use membrane filtrations, which are very expensive. So there is a need of how to just make this system more like earth abundant materials to bring into the system, and as an adsorbent to treat this textile wastewater. And the sixth one is my aerosols to replace GAC is nothing but the granular activated carbons. As we know, like these granular activated carbons are the industrially used adsorbents, and it's from the carbon based source. So we are trying to design or make these aerosols. Aerosols are, I'm going to explain this much further, right? But just aerosol is like a sponge materials which can remove the pollutants, leaving your waste, leaving the water as such. By that way, you reduce the carbon footprints, and also you can have more water regeneration possibilities. And here it's very selective. The aerosols can selectively work on persistent organic materials, which is more on organic compounds, and contaminants persisting like pesticides also, we can just remove it. But it's in a very lab scale system. It's not in commercially worked on, but it's very lab scale system. And the next one is the developing eco-friendly microfiltrations, MF, UF. UF is nothing but ultrafiltrations membrane with sustainability, reusability, and biodegradability. So when you say about the membranes, we all know like there are like different types of membranes available in the commercial markets, but what happens after the usage? So it's dumped in some solid waste place, and after that they just do incineration to discard these membranes. But incineration is not a advisable technology, or it's not a sustainable technology. So what they do currently, the research is going on to develop a membrane which is biodegradable. So after the usage, after the filtration process, when the membrane is not able to filter further, or it's clogged, or it's like it's completely used, it just has to be biodegraded by itself or by some biologically system like MBR system, but it needs to have a biodegradable system. So we are more focusing on cellulose based membranes, which is more compatible, sustainable, and cost effective. And the last one is to replace these RO membranes. So when you say this reverse osmosis membrane, you need to find like it's not that cost effective, even though it's like very efficient, but you say like when you talk about cost effective, it's not that good. And you have a lot of concentrates generated. You have rejection, like 50% of rejections. Like if you use 1 liter of water, you reject 50% of water. Like 0.5 ml you get it for filter, and 500 ml goes for waste. So there is a research going on to develop a alternate technology to replace this RO membrane, and this is capacity deionization is one of the technology. These work with solar energy, so you reduce the energy consumption from 150 bar to something around 1 to 1.5 bar. So it is a huge energy in the wrongs when you say about the long run process. So these are the main themes which we are working right now. And to start with, as I said about the EE2 hormones, which is more focused right now, even in Europe or even in the whole world. So this is an endocrine disrupting hormone, and it's used widely for birth control pills in combination with progesterone. So you can understand how much consumption of this hormone is going. And it's very frequently found in almost all the real water, surface waters. So how to remedy it? So how to remove this particular EE2 hormone? So HETO is detected in surface water like in nanogram, somewhere it's even in ppb, ppm level, and its estrogenic potency is higher than 1.5 times and even 15 times more than the natural estrogens, which are like some beta estradiol and estrone. And there are reports on biodegradation studies of EE2. So biodegradation is one of the technology they have competitive for this EE2 degradation, but the problem is it's time consuming. It's like a huge time consumer on this particular system. And again, the compound is persistent and lower biodegradation rates are observed for EE2. So when you say about the persistence level, it's very less than the natural EE2 estradiols. So there is a requirement of removing this particular EE2, and it should be more sustainable and cost effective, and we need to bring it right now. So we started with of course there are many research working on this particular EE2 hormone, it's not like this, but we thought to try with a combination of photocatalysis employing nano scale magnesium peroxides with in LP, low pressure ultraviolet spectra, followed with small bioreactor platform capsules. So it's a combination of two technologies coming around, like a photocatalysis followed by a biodegradation possibilities. So when we so the spectra you can see in front of the slides is the XRD spectra, which confirms the phase formation of your MgO2, and the band gap, which is more on 4.4. That's the reason we just took to the UV region, UV spectrum. And the advantage of this particular MgO2 is the MgO2 magnesium peroxides have in situ generation of hydrogen peroxides. And when it produces, so what happens is when you generate these hydrogen peroxides, you need to find a UV photolysis to generate the hydroxyl radicals, and these hydroxyl radicals degrade your EE2 hormones. So it's like an advanced oxidation process with the nanomaterials for water treatment purification. And so it depends upon the degradation kinetics dependent on the loading efficiency of your magnesium peroxides and the UV dose. So when I spoke about this SPB, like a smart platform bioreactor, it's we got this from Biocastle. So they are our industrial collaborators. So they developed these biocapsules inbuilt with bacteria for it's like a synonym for a MBR system. When we saw about the MBR microbial bioreactor, which is a huge bioreactors, they made this huge microbial reactor into a capsule phase, and these capsules will be loaded on the wastewater, and this play as the biological system. So their vision is more on to innovate the water treatment methods and to apply these novel treatment methods that are affordable to our clients. So their involvement is to change this bacteria You can just change this bacteria based on your requirements, make a capsule, and the bacteria will be freezed inside, and you need to activate this bacteria when it's used. So as such, the capsules will be freezed and it is inactivated form. So when you want to use, you need to activate these bacteria, and it can work it all by itself. So if you want to understand or follow this more, you can just visit this link which I have given here. You can find more interesting works they have working on, and they are our academic collaborators, and they are also a part of this research. And we found this spectra, like this is the sequential photocatalysis followed by a biodegradation of our EU2. So here you can see, like with UV photocatalysis of magnesium peroxides, it's almost removed, almost around 80% of removal is there in a short span, like 10 to 15 minutes. And after that, you just take the effluent into a small capsule. So it's like a transfer of the system. Like when you have a treated UV photocatalysis system, after 10 minutes, you are taking into a biosystem. So by that way, what happens, the loading of this biodegradation reduces, and the kinetics, the time reduces, and the degradation efficiency is so high. So why, there is a question like, why you want to have two when you can just increase the timing of your photocatalysis to degrade up to 100%? Of course we can do that, but the thing is, you need to find like the COD and the BOD when you say about the chemical oxygen demand and the biological oxygen demand. So the BOD needs to be higher. The biologically biodegradable system of your UT or any pollutant needs to be higher in ratio. For that, you need your biodegradation system to withstand this. So that's the reason we combine this system with UV photocatalysis and biodegradation. So this is the graphical scheme. You can see here. This is the whole system is photocatalysis with MgO2. So first phase will be pre-treated magnesium peroxide EE2 in UV, low pressure UV. Then this effluent is transferred to the capsule system, and here you have your degradation products coming around. And this is a combined technology of photocatalysis and biodegradation process. So after that, so when we have that system worked out, we published that paper in Materials. Then we understood like we need to find some another visible photocatalyst which can work the EE2 removal. And then we found this graphitic carbon nitride, which is again a new generation of photocatalyst, a non-metallic polymer. And we found this system, it's very cost effective. It's compatible to titanium dioxide, which is commercially used as a photocatalysis mainly. So it's really a environmental friendly, visible region, active, and you can modify its band gap, which is very much resembling our solar photocatalysis band gap range. And also the materials can be easily prepared from simple cost-effective materials like melamine, urea, thiourea, etc. So all you need is the system needs to have carbon nitrate. And so here this image, as I've given here, I'll summarize here. So GC3N4, which I say is like the bulk material, like it's an amorphous. You can see from the tab, it's amorphous phase. And when you take this material into a hydrothermal treatment process using a precursor ammonium hydroxide, and you enhance your crystallinity nature of these materials, and you find these materials becoming more surface modified, crystalline, and assisting the enhancement of EU2 degradation. So we found this crystallinity, we proved this data by PXRD spectra. We saw like the GC3N4 one is the bulk GC3N4, means without treatment with hydrothermal. So 2, 3, 4 is like treated with hydrothermal, and GC3N4 2 is with DI water alone, and 3 is with ammonium hydroxide, and this one is 3 GC3N4 is with acetic acid. So when we change the precursor with respect to hydrothermal treatment, you can see the crystallinity of the material enhances. So here we saw like the GC3 is the best one which gave, and the band gap supported the data of PXRD, providing the 2.95 electron volt. So when we studied the visible process scheme, like the experimental condition, we found like ammonium hydroxide based GC4 was giving the best results. So the proposed scheme is more relevant like this. We can take this GC3N4 material, it's a carbon nitrate materials. We modify the band gap based for our solar system, and you make your E to degradation based on different modification. Like if you can see like the kinetics changes. So you can see here with the GC3N4 it's almost 30 minutes it's degraded, and we have also found like the pathway, the degradation pathway of this particular system with complete mineralization, and the whole work can be found in this particular journal which we published in 2020 in hazardous materials. So now the next level of the work is to make it into a photocatalytic membrane reactors. So when I spoke about graphitic carbon nitrate, it's a visible photocatalyst, and by hydrothermal we enhance the crystallinity for degradation of this particular EE2 hormone, and this EE2 hormone's degradation is well enough for real hospital wastewater. Also, we tried with real hospital wastewater. We collected the hospital wastewaters from the local Israel hospitals, and we checked with the analytical system, and we found that it's working. And the proposed mechanism for degradation of E2 was also submitted in the paper. And we also studied the estrogenicity removal. So it's not only the chemicals part we also studied the estrogenicity removal using YES assay. So which also confirmed the complete mineralization, and the material was able to regenerate the same efficiency, like hardly 10% of efficiency lost during the 5 cycles, but probably it was much better. So now the next level, this is how the stack ratio of this particular material looks like. You can see here the geometric of the GC3N4. It looks like the stacked level, like a graphite system. It's a sp2 system. So now what we are doing is, right now we are trying this catalyst onto EPD technology like electrophoretic depositions. We are depositing this catalyst onto a nickel foam using this EPD technology, and after that we are just trying to inbuild into a photocatalytic membrane reactor. It's a lab scale setup. You can see here the whole process. So you have your membrane and you have your feed water. So it goes like this. It's a cross flow system. It goes, and it can also be dead end. So FC1 and FC2 is like a different two processes. Like you want to check the dead end process or the cross flow. Cross flow is nothing but the wastewater passes through the membrane, passes through the membrane, and the dead end it's get into the membrane pores, like it's dead end, like it goes perpendicular, not like horizontal. So this is the pilot scale setup. We worked on one of the project, the European projects, the NATIO-MEM. So we worked on this. So you can see like these are the stack of your layers. You can just make it as a stack layers of your photocatalytic membranes, and you pass your effluent, and through this it goes and you get your reactions. It depends upon it changes the dimensions with respect to your kinetics. Like if you have more time to be required, you change your flow of path, you change the flux, you change the pathway, everything. It depends on the complete ratio of the pollutant concentrations. So the next thing is about the aerosols. So this was very new for us when we worked on these aerosol based materials. After it's been almost 1.5 years we are working on this particular material. So it's like a very sponge, and it's like air dense. You cannot. It's not a heavyweight. Like it's a like air dense, and it's very sponge kind, and it's having a high surface area. So what happens is like even 1 gram of these materials can have a surface area larger than a tennis pitch. So the intention was very clear. Like we just wanted to replace this a particular aerogel based materials to compensate or give a competitive for granular activated carbons for the industrial or commercial purpose. So, but the precise process is a little tricky. But there are different types of aerogels. The most commonly used is silica aerogels, which is held entries in Guinness World Records as well. Best insulators. There are many companies working on these silica aerogels, even for the Boeings and space research centers. They use these silica aerogels for making their system more light, dense, and sustainable. And it's like the best insulators right now. And now the research is more towards them developing into a carbon-based materials, types of aerogels, and they are more covalently bound together, and their surface area ranging between 400 to 1000 meter square per gram. And this carbon-based materials is really interesting because you have carbon and you have a porous, you have insulate, you can make into any system which needs to be doped. And again, about the metal oxides aerogels are used as catalyst in various chemical reactions and transformation for other materials, and it generally enhances worked as a dual functional for a photocatalysis as well as adsorbent. So what the intention is to absorb the material and then play as a photocatalysis. So this is the application for the metal oxides. Then about the polymer, which is much lesser used because mainly polymers are used for their membrane-based systems. So hardly they use these aerogels polymers. And this is again the cellulose-based materials are again used because you can develop this cellulose from a biomass. Like you have plenty of biomass around your system, so you can make biomass cellulose aerogels, which is more flexible, and it also have biodegradable system. So compared to metal oxides where you have metals inside, you cannot use for environmental based applications unless it's a closed system. But cellulose, of course, you can use it for environmental based applications because it's much more environmental friendly and it's more available. So the synthesis of aerogels are very common. It's a three-part mixing of chemicals, then gelation, and the supercritical drying. So when you say about mixing of chemicals, you mix the ingredients based on your interest. Like if I want to work on cellulose, then I make cellulose system. Then the thing is like you need to find the hydrolysis and the condensation. There is a two-phase mainly followed, and the supercritical drying. Generally, this is the main part for the aerogel form because if you dry as in oven, it's not gonna work on. It's just gonna have your materials dried. That's it. You will not find your aerogels. So supercritical drying is again it takes a lot of time to explain on that, but it's a carbon dioxide supercritical drying, which you supply liquid carbon dioxide in a particular pressure to reach this particular carbon dioxide into supercritical conditions. It's around 73 bar. So when it reaches, it becomes supercritical, and there is a solvent exchange happening. And after that, the materials become more fluffy and it becomes more flexible. So what happens? The material will not lose its property, whereas it enhances your porous system, it enhances your adsorption efficiency. So, but the thing is, the main problem now right now they're facing is the expensive. It's very expensive. Supercritical drying is very expensive, and now we are trying to find a room temperature drying possibilities. So we managed to find a application out of these aerogels when we started to work on this particular aerogels. So there is a company called Cabot, aerosols from US. So they are mainly preparing the aerosols. So they are only on Lumira aerosols granules. So to start with, we just wanted to work with some commercially available aerosols. So we try to start working with the chemotherapeutic drugs and the phthalates, which is microplastics. So right now, this microplastics and chemotherapeutic drugs are like emerging contaminants by itself. Like by microplastics, how much problems is there. So we thought we wanted to work with hydrophobic coatings, silica aerosols, and it really worked good. Like the removal efficiency was so high that and also the reusability possibilities. So you can see right here, it's amorphous phase. We confirmed using the XRD, and also the FTAI confirms the functionalization of the materials. And this graph, this is where I just wanted to explain a bit. So when I spoke about the aerosol as such, you can see the absorption of these three chemotherapeutic drugs, and they are like DEP is diethyl phthalates. Phthalates is nothing but microplastics, which is very commonly present in the wastewater. Dox is doxorubicin. It's again one of the chemotherapeutic drugs from the hospital waste effluents, and paclitaxel. So these three drugs we just started to work on with to give an initiation, and we found when you use as such the aerosol, the absorption system is very less. The removal percentage hardly 30 for this, and 10% and hardly 5% for tax. But if you activate the system, activate when I say is just flush with ethanol, the aerosol, you see the aerosol system, the removal of pollutants is high. So the theme behind this was to first you have a hydrophobic aerosols. You need to activate the functional groups present on the surface of this particular aerosol for selectively absorb these micropollutants onto the aerosol system. So we also studied with different drugs, chemotherapeutic drugs for the real samples. You can see here you have different 5 pollutants. These pollutants are really present on the real wastewater. So it's the ratios are a little bit in ppb and ppm levels, but it's there. These are the absorption efficiency, absorbed percentage, and you can see germicitabine, doxorubicin, dexamethasone, paclitaxel, diclofenac. So these are the mainly compounds which is present, and we proposed the prototype 1 for the regeneration of aerosol. So you can see you regenerate. So when you have this system of 1 ppm each, we tried with a colorants, which is rhodamine B, and the pollutants, the chemotherapeutic drugs, all together. We just poured into its system. You can see it completely removes the aerosol, completely removes it, and this aerosols can be regenerated using the ethanol. So the prototype was very clear for the commercial purpose and also for the real-time applications, because aerosols cannot be used for real-time for a one-time system. You need to demonstrate the efficiency of this particular aerosol for multi-times, at least for 5 to 6 times, to compensate the cost of synthesis of this particular material. So we found almost 5 times the regeneration is happening, and for some chemotherapeutic drugs it was almost for 10 to 20 times, and the results are yet to be published. And so now the system is mainly focused on developing aerosols with carbon molecules, and also the activated carbon, and ordered mesoporous carbon, and carbon nanotubes, activated carbon fibers. So these are the mainly focused aerosols based materials, mostly on the carbon phases. So our role is to combine the carbon based materials with nanoparticles. It can be copper or nickel or aluminum oxides, known for high conductivity, and achieve minimum recombination effect. So when we talk about photocatalysis, you need to have a minimum recombination effect. The electron hole pair should be less, so that you will attempt to generate reactive oxygen species. So this is again the process which is that we are working on. And the next one is to replace the reverse osmosis membrane using capacitive deionization. This is what I said. So when you have a system with so much of a high efficient, highly renewed, like it's reputed, like the RO membrane, everybody knows. But now, right now, from last 5 to 10 years, there is a alternate technologies coming around for this RO membrane because of their concentrate and high energy consumption. So capacitive deionization is an emerging technology, almost emerged, and it's mainly on charged ions from saline waters. So the main focus is desalination. That's it. So we can use this for a desalination of for drinking water or irrigation purpose. Can use it, and it's like electrochemical system with electric double layer capacities. So mainly it's focused on charged ions and bacterial cells to absorb. So when you have charged ions like sodium chloride and Na plus Cl minus, so what happens when you pass this saline water into this, you have your nanomaterial sheet followed by a carbon materials and electrode sheets. So you separate you have a different electron charged barriers. So when you have this particular system, the positive, this chlorine goes here and sodium comes here at particular potential, hardly 1.2 to 1.5 volt. It's very less potential, you need voltage. And again, when you reverse this voltage, the current, you can discharge these ions and you can reuse this material. So it's like continuations, you can use this. And this particular system we are trying to work out with the aerosol based materials, because the aerosols, as I said before, it's very high porous. So if you are able to make it into a conductive system with high porous, then it's always good. And this is our lab system which we are working on, CDI. Here we have your CDI placed for wastewater to regenerate the whole wastewater. Now the membrane desalination technologies, as I said before, it's effective pre-treatment. You need a lot of harsh chemicals to pre-treat it, and it's well conventionally pre-filtration is available, and as I said, high energy cost and concentrate management. So you need to find many things on this particular system. I would like to thank my funding agencies and industrial collaborations. So these are our funding agencies which we are working together, which are very helpful. And we're also working on with IIT Madras on Spark project, MHRD's projects. We are working on it, and so mainly. So I think I have completed my talk, and if anybody have anything to share or if you have to interaction, I would love to talk further. Thank you.
Thank you, Vinod.
Participants can wish to post their comments and queries, please.
So Vinod, I have a few questions.
Sure.
Can you hear me? Yeah, so my first question was, what exactly is ozone technology, which you mentioned in the first slide?
Okay, so ozone technology is it's again an advanced oxidation process. It's also a technology it's more on direct oxidation. It's like when you talk about hydroxyl radicals, superoxide radicals, it's like a secondary hydroxyl. But ozone technology is like you have oxygen, and it's you give it changed into ozone system.
Okay.
and it needs to be in closed system. You cannot work it out on the open system. It needs to be closed system, and in presence of oxygen you work on this ozone, and it's very expensive. It's not, but nowadays the technology has been reduced by a lot, but you need to have the ozone technology worked only in the closed system.
So yeah, and my another question is on the capsule which you mentioned. So what kind of bacteria do you use? Because you said bacteria was a bit excited.
We worked on reso factor, I think so. Reso factor kind of bacteria. Actually, it's a patented one. So we are not. I don't know exactly on which thing, because it's more on Rhizophilia, fecal something. That I'm not sure about the bacteria name. Sorry. But you can find the details from the website which I have given on that. They are working more on this biocapsules. Yes.
Okay. And how does it get activated? Once you put it in water, or how is it?
No, actually they activate it in the ethanol stream. Like they make it into a 70% of ethanol with growth something. They grow the bacteria in a periodic time. It takes like 6 to 10 days. The whole bacteria needs to activate it, and once it's activated, we can use it for a bioreactor system.
Okay, it doesn't get activated by itself. It has to be activated, and then
it's in a freeze state. So when they bring to us, it's a freeze state, and they have a protocol how to be worked, and it's a simple one which we can even try on by ourselves.
Okay. And there's a question from one of the participants. So they are asking, like, the thin film materials, like they're considered for microplastic removal. Some starch film material, is it that?
Sorry, I didn't understand.
So the question is asking from Harshak. Now he's asking, thin film-like materials are considered for microplastic removal, I guess.
Thin film materials.
Yeah.
So
thin
when with this
materials, he's asking whether they are considered for the microplastic removal.
It depends upon the material's property. Like if you want to, thin film is like one type of, you are making the materials into a particular nature. Like if you want to make it into a thin film, you can do it. If you want to make it the foam, you can do it. But it depends upon the property of your materials. It needs to be hydrophobic. It needs to be activated. It needs to functional. Which functional group they are using it. So these things are mainly emphasized rather than on. Of course, you can use it on. If you want to on thin film, of course you can use a thin film. But the property of the material is important. Sorry.
Is it a starch-based film?
When you use starch, then you need to be sure like it doesn't dissolve in your water, because the water system do have it gets dissolved. The starch can get into dissolved phase. So you need to make sure it's more hydrophobic, because I believe like microplastics can have more adhesive onto the hydrophobic system rather than hydrophilic system.
Okay.
And they're asking if it's also for cellulose.
Cellulose we can work on for sure. We can try to work on with cellulose. We can try with cellulose.
Okay. We'll wait for some more questions.
I have one more. So the Lumira aerogel which you mentioned, it absorbs the drugs and the phthalates, right? So how do you deactivate it, or how is there a chemical reaction going on which degrades the chemotherapeutic drugs and the phthalates?
Generally, like we're working with few industries here. So some chemotherapeutic drugs are so expensive. Even with 1 mg it's around $500 to $1,000. So what they use is, like, if you are able to reuse this particular chemotherapeutic drugs as such using the FDI probes. So if you are able to do it, then it's by itself, it's really a sustainable technology. But there are few pollutants which we don't want. So of course you can pyrolyze it. You can just incinerate in the system, and you can just reuse the aerogel by itself. But again, we should be very sure about the temperature at what you need to pyrolyze your system, because your functional molecule should not get degraded. So that is the key point.
Okay. There's one more question from the participant. So the question is from Raja Lakshmi. She is asking, can you please update here about what kind of cellulose biomass you have encountered while going through the literature study?
Going through it field. Okay, so which type of applications they are looking for? Whether it's for like, what's the application? Because generally we work with different applications. So if they want to work on microplastics, then they need to find more on a hydrophobic system, which is nanocellulose. We are working more on nanocellulose, so which can be commercially available, but I don't know whether they are preparing the cellulose or they want to purchase it. So microcrystalline cellulose is there, nanocrystalline cellulose is there. And again, as such, cellulose you cannot use. You need to oxidize it. Like there are like few treatment process. You need to modify the cellulose according to your application pattern.
Okay. So if there is no more question, we can end the session.
Yeah, I'm just waiting for any more question, or else we can just end up with it.
That is a chat.
Okay, there's another question from Rajalakshmi Ravi Bhatt.
Trapping on nanoparticles so that it will be better. So generally with cellulose, you cannot trap the nanoparticles because nanoparticles are very less in size. So what I suggest is like you can make it into a metal organic framework kind. So you need to find a chelating ligand, something like EDTA, or which can trap the nanoparticle metals, and followed with cellulose. And again, the cellulose needs to be functionalized. It depends upon which type of, whether you need to oxidize it or reduce. So mainly you can oxidize the cellulose. So there are many literatures available with oxidation of cellulose. So even the Humber's method, you can use it to oxidize your system. So once you oxidize it, then you take your cellulose, oxidize cellulose with your so-called metal, and then try to make it into nanoparticles, because nanoparticle as such you cannot use it for trapping your material. I hope it worked out. Otherwise you can even put to my email ID more questions if you want. I can try to answer it more elaborately. Even I can send few articles relevant to you. No problem. As with any other technology.
Participants can direct their questions to the email ID if needed for elaborate answers.
Is there any toxicity as with any other technology? Is a toxicity about cellulose, like of course when you talk about nano, then again there is a toxicity possibility is there, but it depends upon which type of materials you're gonna use. Because when you talk about different like zinc, titanium, silver, they are toxic in environmental applications. If you talk about environmental scientists, they will say like it's a toxic. But again, that's the reason I was more emphasizing on developing into a metal organic framework, because the intention is very clear. You need to use your materials for a photocatalysis or something to work as a semiconductor. So we can focus on to make it into a system. Otherwise, you need to make a coating system, like as I said, EPD technology. You can just deposit these nanotechnology nanomaterials onto some kind of membranes like nickel foams or even cellulose sheets. You have cellulose sheets, carbon sheets available in the markets. So with EPD technology is like one of the emerging, or even it's a well-known technology for coating system. So you can use that technology. Even spray pyrolysis, spin coating, these things are very good. Just make sure like your nanomaterials doesn't itch out from your system. That's the main criteria for the environmental system.
Thank you, Dr. Vinod, for answering the questions for our participants. And I hope we can just conclude this session.
Okay.
On behalf of Ryan Publishers, I take this opportunity to thank our resource persons for the time and effort taken to prepare the presentation and for conveying new and valuable insights from the current topics related to nanotechnology. And my heartfelt thanks to all our participants for attending this session, and I hope this was useful and informative. Kindly participate in our future events and do subscribe our YouTube channel and share a word about this. I would like to thank Dr. P.F. Stephen for organizing this webinar and our convener, Dr. Reactors as well. Signing off for now. Thank you, everyone.
Okay. Thank you.
Thank you.
Thank you, Vinod.
Thank you, Dr. Vinod. Thank you so much
Thank-
for accepting our invitation. And thank you, Dr. Rainey, program convener of this webinar. Thank you so much. Thank you, Shalini. Thank you. Thanks to all the participants also. Thank you, one and all.